Hello everyone, my name is Anastasios Aivazis,
And I'm George Angelidakis.
and today we're presenting to you TACET, a hybrid semantic and acoustic approach to turn-end detection in spoken dialogue systems. That's a technical title, but the idea behind it is very human. It's about teaching a voice assistant, something we all do without thinking, and knowing the exact moment someone has finished speaking. Over the next 20 minutes, we'll show you why that's surprisingly hard and how existing systems fall short and how our system, TACET, tackles it. So let's first begin with the problem. Every voice assistant is really juggling two questions at the same time. The first is, what did the user say? Which means the transcription. The second is whether the user actually finished. Modern speech recognition has become extremely good at the first question. But the second one is quietly ignored by most systems, and that's where the friction lives. If the assistant misjudges in one direction, it answers early and grabs a half a sentence, so you get an incomplete command or a broken prompt. If it misjudges the other way, it just sits there in silence, and the whole interaction starts to feel slow and unnatural. Both failures come from the same missing capability, real turn and detection. So, how does the industry handle this today? The dominant solution is very simple. The system just waits for a fixed window of silence, and once the timer runs out, it just assumes you're done and replies. It's fast and cheap to compute, and it's trivial to deploy, which is exactly why it's everywhere. But it carries one major flaw. The model is language blind. It reads every silence identically. Half a second pause while you gather your thoughts looks exactly the same as a half second pause at the end of a finished sentence. And that's the heart of the matter. A single acoustic timer is trying to solve a problem that is fundamentally linguistic. Silence alone simply doesn't carry enough information. And that's the gap TACET is built to fill. Our core concept is what we call evidence fusion. Instead of relying on sound alone, we combine the meaning of what was said with the sound of how it was said. To do that, we use a deliberately decoupled architecture with two distinct parts. First, a neural semantic engine that estimates whether the spoken words so far form a complete thought. Second, a rule-based acoustic gate that decides whether it's actually safe to respond, look at active speech, how long the user has paused, and whether their pitch is falling. And importantly, TACET isn't just a classifier in a vacuum. It's a complete end-to-end application. It captures live audio, streams partial transcripts, scores completion incrementally in real time, and generates a spoken reply through a language model and a neural voice. And it all runs inside a lightweight local interface. So before we go deeper, let's see what came before us, because TACET stands for a lot of prior work. The earliest and simplest tools is capture only one slice of the signal. Silence thresholds start at a countdown at the moment your volume drops, and if the timer hits zero, they assume you're done. As we said, they treat all silence equally, so they constantly interrupt people who are just breathing or thinking. Voice activity detection, VAT, is smarter about noise. It classifies each audio frame as a speech or non-speech, but it also filters out fans, typing, and background hum. That makes the system robust, but it only knows if someone is talking, not when they are finished. On the other hand, we have prosodic endpointing, which analyzes rhythm and intonation. The idea that the statement ends on a falling pitch and the question rises. That's generally useful, but intonation varies enormously in accents, emotions, and personal speaking styles, so on its own is inconsistent. More recent neural methods push this much further, and there are two that matter most to us. TurnGPT, on one hand, is a text-based model trained to read a transcript incrementally and predict whether it forms a grammatically and semantically complete thought. It's genuinely brilliant at understanding meaning, but works entirely from text, so it can't hear your tone or your pauses. We also have voice activity projection, or VAP, which takes an opposite approach. It analyzes raw audio to project upcoming turn shifts, capturing the implicit timing and flow of conversation directly from sound. But it operates without any explicit knowledge of the actual words. So you have one family that understands meaning, but it's deaf to sound, and another one that understands sound, but it's blind to words. And that contrast is exactly what motivates TACET. Our proposed solution treats endpointing as a gated combination of both linguistic and acoustic evidence. Concretely, we bring in four signals: semantics, which is a frozen BERT decoder, which judges whether the transcript forms a complete thought; voice activity, an RMS energy monitor, which monitors whether the user is actively speaking; timing, uh, silence duration that acts as temporal safety net; and prosody, uh, yin-praised pitch tracking that listens for the falling pitch. The key architectural move is that we decouple the what, the semantic prediction, from the when, the timing decision, that keeps every model separate and independently testable, and it is what stops the system from cutting off a hesitation or a breathing pause. Now let's open up the system itself.
So we're going to the slide where we show how TACET is actually built. So we will show you the model architecture first. At the top level, the system is a linear pipeline of single responsibility modules running from microphone input straight through the spoken response. The behavior that makes it feel alive is a continuous rescoring. Every single time Whisper emits a new word, the transcript is immediately re-encoded and rescored, giving us a real-time completion estimate that updates word by word. Notice the division of labor here. The standard tools, Whisper, BERT, the language model, and the text-to-speech, are treated as pre-trained. So that's plug-in input-output components. They isolate the core logic. The real contribution we do and the brain of the turn-taking system is our custom TACET head, the decision gate that drives the fusion. So we're going to speak about streaming speech recognition first. Let's zoom into each stage, okay? First, it is the speech streaming recognition. We record microphone audio at 16 kilohertz and accumulate it across the entire turn. A faster Whisper model, and that's the audio to text, it processes, transcribes that audio roughly every 350 milliseconds. So we get frequent partial updates. And we use two beam sizes strategically. A beam size of 1 for fast, low latency partial decoding while you're mid-sentence, and a larger beam size of 5 for a highly accurate final pass once you've stopped. So, three engineering decisions really shape this stage. First, drift prevention. We intentionally disable context conditioning so the model doesn't start hallucinating a coherent continuation and drifting off topic on a short buffer. Second, dual transcripts. We keep a fast raw transcript that we scored immediately to catch new words as early as possible, and a more stable committed prefix that we use purely for display, so for the UI. Third, hallucination safeguards. A voice activity filter plus a voice audio trigger, which together stop Whisper, our speech to text, from inventing filler words during silence. The last one matters more than it sounds. Without it, the model will confidently transcribe words into total silence. So moving on. This diagram that you see brings that whole stage together. On the left, the input gating and logic. Continuous 16 kHz capture feeding a rolling audio buffer guarded by the voice activity filter. In the center, the faster whisper engine redecoding the growing buffer every 350 milliseconds. And on the right, the two paths splitting out. The low latency raw transcript that exposes new words earliest for scoring, and the high accuracy committed prefix that's confirmed across passes and used for display. So once we have text, it goes through strict normalization, lowercase punctuation stripped, and white space collapsed. This sounds trivial, but it's critical for us. Raw ASR output has no casing or punctuation, so if we trained on clean punctuated text and then run on raw text at inference, the distributions would be mismatched and live accuracy would collapse. Using the exact same normalizer in both places prevents that. The normalized text is then tokenized with BERT base encased, truncated into a maximum of 64 tokens, and passed through a frozen BERT encoder, producing a 768-dimensional representation. And because BERT is frozen, we get a big efficiency win here. We can pre-compute the embeddings once and then train our downstream classifier directly on those cast, in a sense, vectors. That dramatically cuts the computational overhead for us and the client too. So, moving on to the classifier itself, our TACET head. It is deliberately tiny. It's a small perceptron that takes the 768-dimensional input down to 64 and then down to a single value. The hidden layer uses a ReLU activation with a 0.3 dropout rate, and the output uses a sigmoid to turn the result into a completion probability. Our decision threshold is set to 0.44, and Tassos will tell you why. If the probability is above that, the gate considers the speech semantically complete. And because it's on the order of only tens of thousand parameters, it's extremely lightweight and ships with the application without adding any meaningful storage burden to the client. So this is the piece that makes TACET hybrid, the acoustic decision gate. It has three mechanisms. First, an active speech override. An RMS energy threshold of 0.02 detects whether you're currently speaking, and if you are, a response is always suppressed. Second, dynamic silence timeouts. If the transcript already forms a complete thought, the system waits about 1 second of silence before replying. If the thought is still incomplete, it waits a full 3 seconds as a graceful fallback, so it never hangs forever. Third, a prosodic fast track. We analyze the most recent 200 milliseconds of audio with a YIN algorithm, and the pitch drop of at least 12% signals a falling. So turn final pitch. When we detect that falling pitch and the thought is complete, the required pause shrinks from a full second down to just 200 milliseconds. The crucial rule: falling pitch never triggers a response on its own. It only accelerates a decision the semantics already support. So this flowchart shows the completion head and the gate working together as one unit. On the left, the head produces a completion probability. On the right, the gate runs its checks in order. Is there active pitch? Is the thought complete? Is the pitch falling? And those feed the timers that ultimately produce a single decision: respond or keep holding. So once the gate accepts the turn, the system resets its utterance tracking and sends the final transcript into a large language model. The generated reply is spoken back to the user. In our current default, the LLM is Google Gemini, configured with strict instructions to keep replies brief, sentence or two, and for the voice. For the voice, we use a lightweight streaming neural text-to-speech service that needs no local model storage. And here's a point we want to emphasize. Because TACET sits in front of the response stage rather than inside it, it's completely model agnostic. What that means, users can point it directly at the LLM they choose. So that means TACET acts as a dropped-in turn-taking layer. It's plug and play by sense. It can upgrade any conversational field of virtually any AI assistant, not just ours. So here we will show you the full architecture visualization. So input gating and dual beam ASR, the semantic encoding subsystem, the turn-taking gate, and finally, response generation through the LLM and TTS, all the way to synthesized audio.
So now let's talk briefly about how we train the model. All datasets are uniformly shuffled within a fixed seed, split 80 by 20 into training and validation. The semantic head is optimized with Adam and binary cross entropy at a learning rate of 0.001. We train in two phases. In phase 1, the initial training runs with a batch size of 32 for up to 100 epochs and 2,000 balanced samples. In phase 2, which is the fine-tuning phase, it scales up to a batch size of 64 for up to 50 epochs or 20,000 samples. Training halts automatically if the validation loss stagnates for 10 consecutive epochs, and we always restore the lowest loss checkpoint, so we guarantee we will keep the best version of the model rather than the last one. And these are the loss curves. Training and validation loss both fall steeply and then flatten out together, tracking each other closely, which is exactly the healthy behavior you want when training a model. There's no sign of the validation loss diverging upwards, so we're not badly overfitting. So how well does it actually perform in real-world experiments? On labeled text validation data, the initial model reached 99% accuracy, and the fine-tuned model tested on 4,000 samples achieved 96.1. You can see both confusion matrices here. The error we watch most closely is the false positive, predicting complete when the user isn't actually done, because that's the error that directly causes the system to interrupt someone. Keeping the number low is what makes the interaction feel polite rather than pushy. Now, to understand why we picked the T threshold for our gate, this threshold isn't arbitrary, it's a balance. Precision protects us from premature interruptions, recall protects us from sluggish, delayed responses. So this experiment we have here sweeps the gate threshold to find the value that gives us a balanced model. On the smaller 2000 sample baseline, the curves are extremely tight and zit right up near 1, which reflects that easy 99% accuracy on the smaller validation split. On the larger 20,000 sample fine-tuned model, the picture is a bit more realistic. You see genuine separation between precision, recall, and accuracy because it's handling a bigger and more diverse dataset. That reflects the robust 96.1 accuracy from scaling up. And critically, our chosen threshold of 0.44 sits right where it maximizes the F1 score while still leaning toward precision, which is exactly what actually actively minimizes the false positives that cause user interruptions.
So it essentially lets you pause mid-thought without being interrupted. Replies the moment you're truly done. Hello, I'm trying to build a project that has to
Hey, that sounds exciting. What kind of project are you working on? I'd love to hear more details and maybe I can help out.
So ChatGPT interrupted me. Let's see how our model behaves.
I'm thinking about creating a project. It's about semantics on AI.
That sounds like a fascinating and incredibly important project. Exploring semantics in AI is crucial for developing truly intelligent systems.
So I need you to tell me, what should I start from in order to create such project?
Start by clearly defining the problem your product will solve and for whom you are building it. Understanding your target users and their needs is crucial.
Even though the experiments were successful, we want to be transparent about where our system falls short. Our single biggest dependency is Whisper. Because everything downstream relies on its transcript, when Whisper mishears the audio, it can feed the semantic model unreliable, semantically incorrect text, text that differs from what the user actually said. And waiting for Whisper to self-correct across passes adds latency. So it becomes a genuine trade-off. You can have speed, or you can have a well-formatted input, but pushing hard on one costs you the other. But we also have limitations on the data sets. The data set coverage limitation, and the model performs great in some contexts and is noticeably weaker in others. Greetings are the clearest example, as it tends to not only to recognize them as complete sentences. We actually tried to fix this by retraining on a greeting-only dataset, but that backfired actually. The model then started marking any sentence containing a greeting as complete, even when it clearly wasn't finished. So it's a reminder that the fix here is careful, balanced data, and not just the data pointed at the symptom. That leads naturally into where we want to take this. Our first priority is to move to speaker and conversation independent testing splits and to evaluate across diverse accents, languages, and noise conditions, because that's the honest test of generalization. We also want to validate that the dataset is properly balanced with more examples and specifically more negatives, so the model learns to reject incomplete terms rather than just recognizing complete ones. And the promising extension is to feed the speech recognizer's own confidence directly to the gate. When transcription is highly uncertain, the gate will intelligently demand a longer acoustic pause before assuming the user is finished. Looking further ahead, we can improve accuracy by giving the model conversational memory. Short replies like yes or sure only count as a complete thought when they directly answer a preceding question, so context matters. A bigger, longer-term goal is the transitioning to a fully multimodal model, moving away from the transparent rule-based gate toward a single integrated model, and finally joint learning, training the system to learn semantic meaning and acoustic cues simultaneously. This could unlock much higher overall performance. That's a deliberate trade-off. We give up. That's a deliberate trade-off. We'd give up some of the current interpretability in exchange for a smoother user experience. So I'm passing to my colleague.
So let's bring it all together. By treating endpointing as evidence fusion, TACET replaces the basic silence timer with a genuinely multimodal approach. It's a complete, lightweight system. It drives a full end-to-end spoken dialogue loop inside a highly packageable application. Its architecture is decoupled and fully tunable because by separating the semantic prediction from the acoustic decision, every component stays independently testable and adjustable. And that leads to our central claim. Truly natural voice interaction depends on a system that understands both what the user says and exactly how they finish saying it. That's precisely what TACET is designed to deliver. A promising, flexible addition to turn-taking toolkit. Tassos, I'm passing to you.
And that's TACET. Thank you very much for listening, and we'll be glad to answer any of your questions by email.